These are the answers to the ideal gas law and stoichiometry practice quiz. Number 1. A flask with a volume of 3,750 milliliters contains 25.0 grams of oxygen gas at a temperature of 32.0 degrees Celsius. Fill in the table below with the appropriate quantities. Let's start with 3,750 milliliters. We have to convert from milliliters to liters. There are 1,000 milliliters in 1 liter, so we get 3.75 liters. Remember that oxygen gas is a diatomic gas, so we have 25.0 grams of O2, and there are 32 grams of oxygen gas per mole. So rounding off our answer to 3 significant figures, we get 0.781 moles of oxygen. Our next quantity is 32.0 degrees Celsius. To convert that to Kelvin, we add 273 and we get 305 kelvins. So we have to calculate the pressure of the gas in units of atmospheres. That means we're going to use 0.08206 for our value of the gas constant R. We're solving for pressure, so in terms of the ideal gas law, PV equals nRT. P, pressure, equals nRT divided by V. Now all we have to do is just plug in the values that we've already got in the table. And when we do this math, the pressure is equal to 5.21 atmospheres. Again, rounding off our answers to 3 significant figures. All right, let's move on to the next problem. Number 2, a balloon that contains 125 grams of nitrogen gas. Again, that's a diatomic gas. So there are 28.02 grams of nitrogen for every 1 mole. Rounding off our answer to 3 significant figures, we have 4.46 moles of nitrogen. The pressure is 608 kilopascals. We can fill that in the table. And the temperature is 19 degrees Celsius, and that becomes 292 Kelvin. So we're going to be calculating the volume of the gas using the ideal gas law. The value of R that we should use in this case is going to be 8.314 because it has units of kilopascals. And now that we have everything except for volume, let's use the ideal gas law. V equals nRT over P. Plugging in the values, we end up with 17.8 liters. Again, rounding off our answer to 3 significant figures. All right, our next problem, number 3, we have 9,260 milliliters. We'll convert that to liters. So we have 9.26 liters. Helium is not a diatomic gas. The molar mass of helium is 4 grams per mole. So 6.31 grams of helium is equal to 1.58 moles of helium. And our temperature is unknown. We'll be solving for temperature. The pressure is in torr, so when we use the ideal gas law, we'll use 62.36 for the value of the ideal gas constant because it has units of torr. So PV equals nRT. We're solving for temperature. So temperature equals pressure times volume divided by the product of number of moles times the gas constant. Plugging in all those values and rounding off our answer to 3 significant figures, we get 299 Kelvin. All right, let's go to the next problem, number 4. We have 3,290 milliliters. That becomes 3.29 liters. We have carbon dioxide gas, but we don't have the grams or the moles. The pressure is 2.83 atmospheres. The temperature in Kelvin is 304. So we're going to use the ideal gas constant that has atmospheres, so 0.08206. We're solving for moles. PV equals nRT. We're solving for N, number of moles, is equal to pressure times volume divided by the product of R times T. And we get, rounding off to 3 significant figures, 0.373 moles of carbon dioxide gas. Now, to figure out the number of grams, we simply multiply moles by the molar mass, and the molar mass of CO2 is 44.01 grams, and we get 16.4 grams of carbon dioxide. All right, let's move on to number 5. Number 5, it says ethylene is a gas that has the formula C2H4. Carbon has 4 valence electrons. Hydrogen has 1 valence electron. So if we have C2H4, we have a total of 12 valence electrons in our structure. Let's start with 2 carbons, and let's put 2 hydrogens on each carbon and connect them with single bonds. So I've already used up 2, 4, 6, 8, 10 electrons. My final 2 electrons, I'm not going to split them up on each carbon because I want a complete octet for each carbon. I'm not going to put a lone pair on the left or on the right. We're going to go ahead and make a double bond. So there is the Lewis electron dot structure for ethylene, C2H4. And now it says calculate the volume in liters of 47.5 grams of ethylene gas at STP. That's standard temperature and pressure. We've already determined that 1 mole of any gas at standard temperature and pressure has a volume of 22.4 liters. And we'll use that conversion factor in this problem. But first we have to go from grams to moles. The molar mass of ethylene is 28.052. That just comes from the periodic table. Now we'll use 22.4 liters for every 1 mole of gas at STP. And this math will give us, rounding off to 3 significant figures, we get 37.9 liters for our answer. All right, number 6. It says if 1 milliliter is equal to 1 cubic centimeter, calculate the number of liters in 1 cubic meter. So we'll know that in linear dimensions, so not volume but just a straight line, there are 100 centimeters in 1 meter. But if we have a cubic centimeter, I need to actually multiply 100 times 100 times 100, or 100 cubed. That's going to be 1,000,000 or 10 to the 6. And if there are 10 to the 6 or 1,000,000 cubic centimeters in 1 cubic meter, I can replace cubic centimeter with milliliter. Now all I have to do is convert milliliters to liters. Remember, there are 1,000 milliliters in 1 liter. So 1,000,000 divided by 1,000 is equal to 1,000. So the correct answer, there are 1,000 liters in 1 cubic meter. All right, moving on to number 7. A sample of pure sulfur hexafluoride has a volume of 2.25 cubic meters at STP. We're going to calculate the mass of this gas sample in units of kilograms. We have several steps to do. Let's take it one step at a time and focus on the units. Starting with 2.25 cubic meters, we just learned in the last problem that there are 1,000 liters in every 1 cubic meter. Now we can go from liters to moles because we're at STP, standard temperature and pressure, 22.4 liters in 1 mole of sulfur hexafluoride. Using the information on the periodic table, we can get the molar mass of sulfur hexafluoride, which is 146.06, and then finally going from grams to kilograms, there's 1,000 grams in 1 kilogram. If we do this math and round off our answer to 3 significant figures, we get 14.7 kilograms. All right, let's take a look at number 8. Calculate the density of butane gas, C4H10, at STP in units of grams per liter. So we know that on the periodic table we can get the molar mass of a gas. So if we do that for butane, there are 58.12 grams of butane per mole. We also know that there are 22.4 liters of butane gas in 1 mole because we are at standard temperature and pressure. So with these 2 conversion factors multiplied together, the moles cancel out, and we end up with units of grams per liter. and that's what we want. So the density of this gas is equal to 2.59 grams per liter. All right, let's take a look at number 9. A certain gas contains carbon, hydrogen, and fluorine. Calculate the molar mass of this gas if it has a density of 2.32 grams per liter at STP. Let's use 22.4 liters over 1 mole. And if we multiply these two quantities together and the liters cancel out, we end up with 52.0 grams per mole. Now that is the molar mass of a substance that contains carbon, hydrogen, and fluorine. Let's see if we can figure out what the formula of this particular gas is. Carbon has a mass of 12, hydrogen has a mass of 1, and fluorine has a mass of 19 on the periodic table. If we know that carbon forms 4 covalent bonds, we could start with 1 carbon, 3 hydrogens, and 1 fluorine. Now the mass of this formula is equal to 34 grams per mole. Let's replace one of the hydrogens with a fluorine. Now we have 12 plus 2 plus 38. That's exactly the molar mass we're looking for. And just to see if we had 2 carbons and 5 hydrogens and 1 fluorine, that molecule comes close, but its molar mass would be only 48 grams per mole. So the correct answer for number 10 is the chemical formula CH2F2. All right, let's take a look at number 11. Calculate the number of molecules of oxygen that are present in 27.5 milliliters of O2 at standard temperature and pressure. We'll start with 27.5 milliliters. We know we can use 22.4 liters per mole. Let's first convert milliliters into liters. Then we can use the conversion factor from liters to moles based on the fact that we're at STP. We can now convert from moles into molecules using Avogadro's number. And if we do all of this math and round off our final answer to 3 significant figures, we get 7.39 times 10 to the 20 molecules of oxygen. All right, the next question, number 12, involves an unbalanced chemical equation. Let's go ahead and balance that. There's already 1 nitrogen on each side, but there are 3 hydrogens on the left and 2 hydrogens on the right. So we could start with putting a 2 in front of the ammonia, NH3, and a 3 in front of the water. Now we have 2 nitrogens on the left, so we can put a 2 in front of the nitrogen monoxide. And if we add up the oxygen atoms on the right, we have 2 plus 3, which is 5. I might put 2 1/2 or 5 halves in front of the oxygen as a temporary coefficient. Then if I multiply each and every coefficient by 2, my final whole number coefficients are, from left to right, 4, 5, 4, and 6. If we convert from liters of NH3 into liters of oxygen, this can be done in one step. Remember that if we have 2 different gases at the same temperature and pressure, moles and volume are proportional. So therefore, instead of using mole ratios, we're going to use volume ratios. And we take the coefficients, 4 and 5. So we start with 3.45 liters of NH3, and we convert into liters of oxygen using the coefficients from the balanced chemical equation. So our answer, rounded off to 3 significant figures, is 4.31 liters of oxygen. All right, moving on to number 13. A sample of gas has a mass of 26.5 grams, but we don't know what its formula is. We have a volume, 4.25 liters. We have a pressure, 275 kilopascals, and we have a temperature, 35 degrees Celsius. If we have a volume, pressure, and temperature, let's calculate the number of moles using the ideal gas law. N equals PV over RT. Now the pressure is in kilopascals, so we'll use 8.314 for the ideal gas constant. We do have to convert 35 degrees Celsius into Kelvin by adding 273. So I have 308 Kelvin. And if we do this math to get moles, 0.4564. I didn't round off the final answer yet. I included an extra digit for precision, but we're not quite done because it says calculate the molar mass of the gas. Molar mass is grams divided by moles. So 26.5 divided by 0.4564. Our final answer is 58.1 grams per mole. And that was it. We're not going to be identifying the formula of that gas, but the molar mass is 58.1. All right, let's take a look at number 14. Calcium carbide, CaC2, reacts with water to produce calcium hydroxide. Now the charge on hydroxide is -1. The charge on calcium is +2. So it's going to be CaOH inside parentheses 2. And then finally acetylene gas. This is almost balanced. We have 1 calcium on each side. We have 2 carbons on each side. But to get 2 oxygens, I've got to put a 2 in front of the water, and now I have 4 hydrogens on both sides. All right, so the equation is balanced. We're going to write the Lewis electron dot structure for the polyatomic ion known as carbide. So the formula of calcium carbide is CaC2. That means that calcium is the cation with a charge of +2, and carbide, C2, is a polyatomic ion that has a charge of -2. There's 2 carbons. Each carbon has 4 valence electrons, but with 2 extra electrons for the -2 charge, we have 10 electrons to work with. I'll start with a single bond between the carbons. That's 2 electrons, and I'll use lone pairs until I get to 10. So 4, 6, 8, 10, and now I have no more electrons. But we don't have a complete octet for either carbon. Let me make a double bond and see if that helps. Well, the carbon on the right has an octet, but the carbon on the left does not. Looks like we have to make a triple bond in order to satisfy the octet for each carbon. So your final structure has a lone pair of electrons on each carbon and a triple bond in the middle. The next part of this question gives us information about a chemical reaction, that calcium carbide reacted with water to produce acetylene gas. The acetylene gas was collected by water displacement. The volume of gas collected was 84.5 milliliters, and the temperature of the water bath was 23.0 degrees Celsius. The atmospheric pressure in the laboratory was 755.8, and you can say millimeters of mercury or torr. The vapor pressure of water at 23 degrees Celsius is 21.1 millimeters of mercury or torr. When a gas is collected by water displacement, we adjust the height of the collection bottle so that the total pressure inside the bottle is equal to the pressure of the atmosphere in the laboratory. Now the gas collected in the bottle is going to be acetylene with a little bit of water vapor. So the total pressure is the sum of these two gases added together, their partial pressures. We know that 755.8 is the pressure of the atmosphere in the laboratory, and that at the temperature of 23 degrees Celsius, the pressure of water is 21.1. All we have to do is subtract. The pressure of the acetylene is 734.7 torr. This is not our final answer because they want the pressure of the acetylene gas in units of atmospheres. Let's convert 734.7 torr into atmospheres. We'll round off our answer to 4 significant figures, and we get 0.9667 atmospheres. Okay, the next part of this question is going to involve the ideal gas law. PV equals nRT. We're going to calculate the moles. So moles equal PV divided by RT. We know the pressure is 0.9667 atmospheres. We're going to use 0.08206 for our ideal gas constant because of the atmosphere unit. We have a temperature of 23 degrees Celsius for the water bath. That's the same as the temperature of the gas, but we do have to convert Celsius to Kelvin. That's 296 Kelvin. The volume of the gas is 84.5 milliliters. That becomes 0.0845 liters. So if we do this math, we get moles of acetylene, and it works out to be, rounded off to 3 significant figures, 0.00336, or you could say 3.36 times 10 to the negative 3 moles of acetylene. And now we're going to take this number of moles of acetylene and convert this into grams of the reactant calcium carbide. Remember, calcium carbide is a reactant, acetylene is a product. So in terms of the conversion factor, it's a 1-to-1 ratio between moles of acetylene and moles of calcium carbide. And from the periodic table, the molar mass of calcium carbide, CaC2, is equal to 64.1 grams. So if we do this math and round off our answer to 3 significant figures, we get 0.215 grams of calcium carbide that was consumed in this experiment. Well, that represents the last of the questions on this practice quiz. I hope that these answers and explanations were helpful. Thanks for watching and good luck studying for your quiz.